Assalamu alaikum. Welcome to this lecture. In this lecture, we'll be discussing about the different numericals which are already asked in different competitive exams. So our focus will be mainly on the numericals which are asked in the GATE, Engineering Service, and our State Electricity Board, usually PDD. They usually conduct the exam through JKSSB. JKSPDC is actually independent. We can say independent company, and JKPSC. PDD is also recruiting the engineers through JKPSC. We will start from the GATE questions which are already asked in the GATE. So let's first start question number 1. It is like this. The nominal pi circuit of a transmission line is shown in the figure. This is X, this is Z, this is X. Usually instead of reactance, we analyze the circuit in admittance of the parallel parameters. So impedance of the circuit is given as 100 at an angle of 80 degrees, and the reactance is given as 3300 ohms. So we need to find out the magnitude of the characteristic impedance of the transmission line. So as we know that the characteristic impedance is given by ZC, that is given by square root of Z divided by Y. So calculating the value of phi, it comes out to be equal to, that is, it comes out to be equal to y. First you need to find out this. Since x is given, x is actually the reciprocal of half of the admittance, total admittance. So y by 2 is equal to, usually this y by 2 will be equal to 1 by x, so that is equal to 1 by 3300, and y will be equal to 2 by 3300. That comes out to be this. So from here y will be equal to this 100, since we are only interested to find out the magnitude. So 100 divided by this value, it comes out to be 406.2 ohms. So this is how you can find out the value of you have to be very careful about finding the value of phi, because this value is the reactance of half of the admittance, not the full admittance of the transmission line. This is one of the GATE questions which were asked in GATE 2017. It was of 1 mark. The next question is regarding the inductance of the line. We have a transmission line whose configuration is given like this, and the system has a frequency of 50 Hertz, and in this case DAB is equal to DBC, DCA, that is the equilateral triangle, is equal to 1 meter as shown in this figure. The resistance of the conductors are neglected. We don't have to calculate the resistance. The geometric mean radius, the GMR of each conductor, is given to be 0.01 meter. So neglect the effect of ground magnitude of, find the magnitude of positive sequence reactance. That means the general reactance we have to calculate, that we are usually doing in the, that we have already done in the class. So it is also given that you have to round it off to up to 3 place of decimal. This is also 2017 GATE question. It was of 2 marks. So as we know, we have to calculate first inductance, or we can directly calculate the inductive reactance. We just have to multiply the inductance by 2 pi f, that's omega. 2 pi f into 2 into 10 minus 7 ln of dm by ds, that is the usual formula that we know. Giving the value of dm is equal to 1 and ds is equal to gmr, that is 0.01. So it comes out to be 2.89 into 10 to the minus 4 ohm per meter. So converting it into kilometers, you have to multiply it by 1000. It comes out to be 0.289 ohms per kilometer. This is very simple. Similarly, another question which is also asked, I haven't mentioned the year of this question, maybe in 2017 or 2018. So an extra high voltage transmission line of length 300 km can be approximated by a lossless line having a propagation constant of this 0.00127 radians per kilometer. Then the percentage ratio of the line length to the wavelength of the line will be given as. So we have to find out the percentage of this 300 divided by the lambda. First we have to calculate lambda. Lambda will be simply equal to 2 pi divided by beta. That's 2 pi divided by beta is this. and ratio will be line length. 300 divided by this is come out to be 6.06%. Sometimes even if this beta is not given, as we know that for 50 hertz line, uh, the value of uh, lambda is usually this 5000, sorry 60 hertz, and for 50 hertz it is 6000. So if the frequency is directly given, then you can use that formula to calculate or to use that value, that is the lambda for 50 hertz will be 6,000 kilometers, and lambda for 60 hertz will be 50,000. So you can use that and to calculate the ratio of the line. This is very simple. I think I have shown you in the class, or I had given you as the assignment. So this is how you can calculate this in the ratio of the wavelength to the length of the line. Now one more question is very simple. This is based on the ABCD parameters of transmission line. A 220 kV 20 kilometer long three-phase transmission line has the following ABCD parameters like this. So its correct charging current will be, so the correct charging current will be simply, you just have to, since it is 20 kilometer long transmission line, usually we neglect the capacitance effect for the short transmission line, but since it has asked you to find out the charging current, so you have to take care of the and also C is given. You can see for this is actually the value of this capacitance capacitive admittance. And as you know that when you are asked to find out the value of charging current, you have to find out the value of this IC, that is equal to V phase divided by XC, or V phase into you can say, or some simply you can use the ABCD parameter. It has used some different approach. As we know, charging current is given by IS is equal to C into VR. So VR is given like this. So VR divided by root 3 multiplied by C. When you change it over here, it will be multiplied to this, and its value will be automatically, you can see over here, 220 by root 3, that is VR per phase, multiplied by this C. The C times VR, it will be equal to 11 by root 3 at an angle of 90 degrees. This approach is not the right one, which it has done. You have to use the ABCD equation, ABCD parameter equation, to calculate it. So one more question regarding the GMR and this GMD. A composed conductor consists of 3 conductors of radius r each. It has a radius r. Their conductors are arranged as shown below. That means 3 are apart from each other at the corners of equilateral triangle, and the side of equilateral triangle is equal to 3r. The geometric mean radius in centimeter of the composite conductor is given to be k into r. It is given to be k. Find the value of k. We need to find the value of k. Since we know that the GMR these are the composed conductor which are in close vicinity to each other, it will be equal to 0.7788 r for this case, multiplied by 3r, that is the distance between these two, and multiplied by 3r, and that is the distance between these two. So here it is not, actually it is for three conductors. As you know that when we have calculated this for the conductors at the place of when they are placed at the corners of equilateral triangle, you have to find out the cube root of these 3 distances only. So I don't know what he has done over here. And you have to, okay, I got it what he has done. That is he has raised to power 3 for 3 conductors, and then he has raised to power it 1 by 9, that's 1 by 3 square. So you don't have to do it like that. You have to multiply these two and take the cube root of these 3. So it will come out to be 1.913 r. So that means, which is already given as k into r, that means this k will be equal to 1.913. So this is how this is very simple. You just have to understand the question and then apply the logic, or we can say concept, that we have already discussed in the class. You can see from these questions, the questions that are asked in the gate, they are very simple and straightforward. If you have been attentive in the class, you'll be able to solve all the questions. And apart from this, you need to have a certain practice on these numericals just to gain the confidence. And the purpose of this class is to make you sure that the level of the gate is not that much that you're going to do. You just have to be very attentive in the class when you will be attending the class and try to do all the numerical that I have given as an assignment or in the class, you will be able to do all these questions. So this question was asked in 2015 GATE and it was of 2 marks. So one question is on the insulators. You can see we have a two insulator string made of the porcelain. The self capacitance of the insulator is 5 times the shunt capacitance between the link, that is, this is MCM is equal to 5. So the voltage across there, we need to find out this voltage E1 and E2. This is very simple. You don't have to go here and there. So here, line to line voltage is given as 11 kV, phase voltage will be 11 by root 3. So E1 plus E2 will be equal to 6.35, that's 11 by root 3. From this figure, I is equal to I1 plus I2. So j omega 5c, that is this, j omega 5c into E1 is equal to j omega. So usually I have in the class I have omitted the value of j because you will see in all the equations this j will be cancelled out. So that means 5 E1 because omega c will also be will also cancel out from the equation. So this will 5 E1 will be equal to 6 E2. So from these two equations, when you solve them, that means E1 is equal to 3.46 and E2 is equal to 2.49. That means option B is the correct one. It was asked in 2010 GATE exam. Now this is also asked in the same GATE exam, that is 2010. So you can see it considered 3-phase, 3-core, 3-phase 50 Hz 11 kV cable whose conductors are denoted by R, Y and B, R, Y and B. The interface capacitance C1 between each pair of conductors is 0.2. This is called the C1. Usually in the class I have denoted this to be C1, that is the capacitance between conductor and sheet, but here it has changed its nomenclature. It has named the capacitance between the conductors as C1 and the capacitance between conductor and sheet as C2. So there is a little bit twist. It is when you have properly understood the proper nomenclature of C1 and C2, you don't have to remember C1 and C2, you just have to remember the actual name, that is capacitance between the conductors and capacitance between the conductor and sheath. So it is given as the interphase capacitance between the pair of conductors, that is this is C1, and the capacitance between each line conductor and the sheath is 0.4. The per phase charging current is, as we know, when we convert this into equivalent star, this will be 3 times C1. So per phase will be C2 plus 3 times C1, that is this C2 plus 3 times C1. So C equivalent will be equal to 1 microfarad. So per phase will be equal to 11 by root 3. So charging current will be equal to J omega C equivalent into P. Omega is equal to this into 1 into 10 power minus 6 into this. It comes out to be close to 2 amperes. Similarly, this very simple question, it is asked in 1999 of 2 marks. For a single phase, in this question you can see we have been given the single phase overhead line having a solid copper conductors of diameter 1 centimeter, spaced 60 centimeter between the centers, that is D. We need to find out the inductance in millihenry per kilometer. So usually when we do the calculation, we use L is equal to 2 into 10 to the power minus 7 into ln of D by R dash. But since you can see there are two values given, that is this and this, that means we have to calculate the internal inductance separately and external inductance separately. So internal inductance will be equal to 1 by 2 into 10 to the power minus 7, is a constant, Henry per meter, that will be equal to 0.05 millihenry per kilometer, and external inductance will be equal to 2 into 10 to the power minus 7 ln of 60 divided by 0.5 Henry per meter, that is equal to 0.2 ln of 60 divided by 0.5 millihenry per kilometer. We don't have to calculate it after this because it is given as it is. So the answer for this is 0.05 plus 0.2 ln of 60 divided by 0.5 millihenry per kilometer. Now this question is about the coronal loss. The coronal loss on a particular system at 50 Hz is 1 kilowatt per kilometer per phase. The coronal loss at 60 Hz would be. So it's very simple, because we know that PC, that's coronal loss, is proportional to 25 plus F. So I have written it for two different frequency, that PC2 by PC1 will be equal to 25 plus F2 divided by 25 plus F1. So PC2 will be equal to PC1 into 25 plus F2 divided by 25 plus F1, 1 into 85, that is 60 plus F2 is at 60. So 60 plus 25 is 85 divided by 75, that is 1.134 kilowatt per kilometer per phase. So the answer will be D. This was asked in 2000 GATE. One more question. It's very simple question. This is asked in GATE 2020. Bus 1 with a voltage magnitude of 1.1 is sending rate to power Q12 towards bus 2 with a voltage magnitude V2 is equal to 1 per unit. So the voltage at different two buses is given. Magnitude of voltage bus 1 is now okay, through a lossless transmission line of reactance X. The reactance of this line is X. Keeping the voltage at bus 2 fixed at 1 per unit, the voltage here is 1 per unit. Magnitude of bus voltage at bus 1 is changed so that the reactive power Q12 sent from bus 1 to bus is increased by 20%. Real power flow through the line and both condition is 0. Real power is considered to be 0. The new value of the voltage magnitude V1 in per unit round up to 2 decimal place at bus 1 is. So we need to find out V1 at increased Q2. So V1, so for a real power 0, that means load angle delta will be equal to 0. We have discussed it because this P is equal to real power V1 V2 by X sine of delta. When P is 0, delta is 0. So V1 is 1.1, V2 is equal to 1. Now Q12, in class we have discussed that this Q1 or QR is equal to V1 V2 by X cos of delta minus V2 square by X. But here, since we have to calculate this at the sending end, this QS will be equal to V1 square by X minus V1 V2 by X cos of delta. Here it is not sin delta, it is cos delta. It is misprint over here. Please try to correct this. Please read it as cos of delta. So this will be V1 square by X minus V1 V2 by X cos of delta. So giving the value of cos of delta equal to 0, it will be equal to 1. That means it will be 1.1 square, that is 1.21 divided by X minus 1.1 into 1, that's 1.1 divided by X. When you subtract them, because their denominator is same, it will 1.21 minus 1.1, it will be equal to 0.11 divided by X. Let's say this is Q12 in the first condition. In the next condition, when this Q12 is increased by 20%, that means this Q12 will be now 1.2 Q12. So 1.2 Q12 is equal to V1 square by X minus V1 into 1 divided by X, because V2 is kept as 1 per unit, and cos of delta is again equal to 0, cos of delta will be 1. So this will be equal to V1 square minus V1 by X, that is equal to 1.2. This Q12 will be equal to 0.1 by X. This will be equal to 1.2 into 0.1 divided by X. This X and this X will be cancel out. This comes out to be equal to V1 square minus V1 minus, when you multiply 1.2 into this, it will be 0.132. Solving this, V1 will be equal to 1.12. So to increase this Q12 by 20%, we have to increase it to 1.12 per unit from 1.1. So this is how this can be calculated. Again, the same formula has been used. You can see how easily you can do this. So the next question is about the cables. A single power core cable having a total conductor resistance of, this is the resistance of conductor 0.7 actually these are two single power core cables having a total conductor resistance of 0.7 and 0.5 ohm respectively. These are two cables, one is this cable and another is this cable. The insulation resistance between the core and sheath that we have discussed already is 600 and 400 respectively. If they are now connected in series, what will be the ratio of insulation resistance to the conductor resistance? So we need to find out the insulation resistance ratio to the conductor resistance. When they are connected in series, you can see these two will be in series. They will be simply calculated as 0.7 plus 0.5, that comes out to be 1.2. So when they are connected in series, these two resistances will be in parallel and they are independent of these resistances. So this R equivalent will be equal to 1 by R equivalent 1 plus 1 by R, sorry, insulation 1 by R1, insulation 1 by R2, insulation is 1 by 900 plus 1 by 60, it comes out to be 360 ohms. So their ratio is 360 divided by 1.2, that is 300. This question was asked in GATE 2021. You can see how simple the questions are. There are various questions asked about the power system. Since we have not covered yet. I'm only discussing those questions which are related to the chapters that we have discussed so far in the class. Now, these were the questions which are asked in the gate. Now we shift to the another exam, that's the engineering service exam. So one of the questions that were asked in engineering service examination 2018, the time interval needed for a surge to travel the end of 600 kilometer long over a transmission line is, we need to find out the time. As we know, uh, the velocity of the voltage wave or current wave is approximately equal to the velocity of the light. So you can find out the time. That means this time will be equal to distance to velocity. Distance is 610 to the power 3 meters divided by 3 to 10 to the power 8 meter per second. You can get the value of time. That will be 2 milliseconds. So this is how you can calculate, and this is how you can approach this type of problem. And you see that how much easy these problems are if you have a proper understanding of the subject. One more question. An 11 kV three-phase transmission line has a resistance of 1.5 ohm and reactance of 4 ohm per phase. The efficiency of the line supplying the load 4 megawatt at 0.8 lagging power factor is. Since it is not given whether this is a long transmission line, short transmission line, or it is medium transmission line in terms of length, since you are given 11 kV, you can assume that this is a short transmission line. When this is given, that means source current and this line current, so source current and receiving end current will be same, and I have denoted by IL. So calculating IL will be equal to power divided by root 3 divided by the voltage divided by the power factor. It comes out to be 262.432 amperes. Now what will be power loss? That means power loss in the resistance. I forgot to mention here into 1.5. It is included that this was 0.206. So this will be 3 into 262.432 square into 1.5 ohms. It comes out to be 0.206 megawatt. So total input power will be equal to, or you don't have to calculate input power. So efficiency will be equal to output power divided by output power plus losses. It comes out to be 95.08. So this will be it is. This option will be the correct option. So this way also you can approach. There are other approaches where you can find out whether this is going to be there are other approaches where you can find out its value. So like to calculate directly the sending in power. So in that case you can do that as well. Actually there is a slight modification. Please try to multiply here 1.5. So these losses come out to be 0.31 megawatt. You can see here I have forgot to multiply this resistance. When you add 0.31, it doesn't come as 95, it comes out to be 92%. Please try to correct it. I don't know why I have forgot this, but the approach is the same. Like I have done is, only thing I have mentioned, I have forgot to mention here, to multiply 1.5. This is very important. So here its option is now 92%. So this question was asked in 2018 engineering service examinations. Now one more question, which is very simple question, again asked in the same examination. A lossy capacitor CX rated for operation of 5 kilovolt 50 Hz is represented by an equivalent circuit with an ideal capacitor of Cp in parallel with the resistance Rp. Cp is equal to this and Rp is equal to the power loss and the 10 delta of the lossy capacitor when operating at the rated voltage are respectively. We have to find out the power loss, total power loss, and the 10 delta. Cp is given as this, Rp is given as this, V is given as this, and frequency is given as this. From this triangle, as we have already discussed in the class, this equation, so the cable can be represented by this circuit, and this is this phasor diagram. So tan delta will be equal to this perpendicular, that is IR divided by this IC base. IR is equal to V by R divided by V omega C. V and V will be cancelled out. It will be equal to 1 divided by omega C into R. Omega C is 2 pi F into Cp and Rp. Here this C has been denoted or represented here by Cp, and R has been represented by Rp. So giving the value of this, tan delta comes out to be 0.025. So power loss, as we know, that is equal to V square omega C into tan delta. V square is given, that is 5 kV. 2 pi f. Now everything is given, you can it comes out to be 20 watts. So the answer will be C part. Now a simple question. A pair of high frequency parallel transmission line has a distributed capacitance and inductance of this and this respectively. What is the characteristic impedance? Characteristic impedance will be simply root of L by C. L is given over here, that is this, C is given in this. So you can get the, it is 0.8 here. You can get the value of this, it comes out to be 110.68 ohms. One more thing, the propagation constant of a transmission line is given this, that this is alpha, this is beta, this whole is actually gamma. The wavelength of the traveling wave. Wavelength you know that is equal to 2 pi by beta. 2 pi is the constant term, beta is 1.5 into 10 raised power minus 3, that is this term. This will be its answer. So one more question, this is related to corona and it has been asked in ESC 2020. In this case, we are asked which are the following factors affect corona: atmospheric condition, temperature, humidity, moisture. This is also the current in conductor, waveform, condition of the surface, conductor, smoothing, and dust. So you know that these are all affecting this. Only thing is that the current in the conductor, which is usually not. Sometimes it is also considered to be, since you can see the options are only 3. So you have to nullify the one which has the least effect of the corona, that is the current in the conductor. That means the option will be 1, 3, and 4. That is B will be the correct option. Now one more question. This is related to the power flow. So in a 275 transmission line with line is equal to line constant A is equal to this, B is equal to this. If the voltage profile at each end is to be kept as 275 kilovolt, the unity power factor, at unity power factor, we need to find out the power at unity power factor. So as unity power factor is given at the receiving end, that means at the receiving end QR will be equal to 0. By using the formula this, VS/VR will be sine of beta minus delta minus A into VR by B, VR square by B sine of beta minus alpha. So QR is equal to 0, VS/VR it is given, and beta delta is not given. Here all the terms are given. So here from this equation we can get the value of delta. So from QR we get the value of delta, and power at unity power factor will be PR is equal to VS/VR by beta cos of beta minus delta. Every constant is given over here, so you can calculate it. It comes out to be 118 megawatt nearly. So I think similar question, very similar to this, we have done in the class. I don't know whether that is identical to this, but one of the questions which we have done in the class, one part or two part are the same. That is part A or part B are the same. Now coming to this was about the national exams. So now coming to the state exams, usually whether that is done by JKPSC or JKSSB. Let us start with the JKPSC exams. Usually JKPSC means the exams that are conducted by the PDD for the recruitment of assistant engineers in electric. Transmission efficiency of a transmission line increases with, as we know that IL is equal to P divided by root 3 into VL into cos of theta. So as voltage increases and power factor in IL decreases for the same power, and you can see the efficiency will increase because power loss will decrease. So that means efficiency will increase as these two will increase. So increase in both power factor and voltage. Skin effect of a conductor becomes more pronounced at higher frequency, lower frequency, DC, low voltage, definitely at higher frequency. You can see in case of JKPSC or JKSLV, the questions are slightly easier as compared to GATE and this engineering service exams. They are actually very easy as compared to them, and they are usually the numerical portion is very less, or even if there is some numerical, they are simple numericals. Now in AE 2017, ACSR conductors have all aluminum conductors made of aluminum. You know, outer conductors made of aluminum, rest are. So that means the correct option is outer conductors are made of aluminum because the middle conductor is made of steel. So for a lossless line, the value of conductance is, as we know, for a lossless line, we know we take R is equal to 0 and G is equal to 0. So here the conductance means G. So G is here given to be 1.732, 0.707, 1.4. So these three options are not correct, means the correct option will be now there. This was asked in AE 2010. So coronal loss increases with increase in frequency, supply, and the conductor size. We know that there are two parameters which are given. One is frequency and a conductor size. We first have to see the relationship between the coronal loss and these parameters. As for the frequency, we know that coronal loss is directly proportional to frequency plus 25. So that means it increases with the increase in frequency. As far as conductor size is considered, it depends upon the two factors: critical disruptive voltage and coronal loss, because radius comes in both the formulas. And we have deduced that when diameter of or radius of the conductor is increased or size of the conductor is increased, coronal loss decreases. Here it is, we need to find out the relationship of coronal loss increase with conductor size and frequency. That means increase in frequency, supply frequency, and reduction in the conductor size. This will be the correct option. What type of insulators are used in 132 kV transmission line? So we need to find out the type of insulators in which are used in either. We know the pin type is used for 132 up to 33 kV. Shackle type is used in 220 volts, and pin and shackle against small wood, that is this type. The other name of suspension insulator is also known as this type in general. And then we separate them, this type as suspension and strain type insulator. Otherwise, the general name of these two is the disc type, because they are of the form of the disc. This is also asked in the AE 2006. So one more question regarding the corona. Corona usually occurs when the electrostatic stress in the air exceeds 30 kilovolt maximum value per centimeter, 22 kilovolt maximum value per centimeter, 11. These two values are not there. We may have this and this value, but you need to find out whether it is maximum or it is RMS. So we know that the 30 kilovolt is the maximum value. That means this is the correct option. If this option was RMS value, this would have been also the correct option. But here it's maximum. That means it has to be. It is not the correct. Correct option is only 30 kilovolt per centimeter. That's the peak value. This was also asked in the AE 2006. Now coming to JKSSB, that means usually JE exam. So actually, I know that there are only 2 JE or 3 JE exam. I don't remember. Perhaps 2 JE exams which are based on the written exam. So one of the papers I had, and I have taken some questions from that question paper. And JE 2016 paper I didn't have, so I have missed some questions from that. If I get in the meantime, I will also discuss these questions also. So this is a question: a single phase 60 Hz generator supplies an inductive load of this at a power factor of this lagging from 20 km long overhead transmission line. The line resistance and inductance are this. The voltage at the receiving end is required to kept constant at 10.2. So here receiving end voltage is given, the line parameters are given, receiving end power is given, length of the line is given. Since the length of the line is 20 km, it's a short transmission line. So we'll first calculate the receiving end current, that will be power divided by voltage into power factor. Here I have not used the root 3 because it's a single phase. So it comes out to be 551.47. So Vs is equal to Vr plus IR into Z. I have not here given the values. I have given the values on the rough and put the value directly over here. And I have also dropped the value of the angle. It comes out to be on the magnitude 12.1. So voltage regulation will be 12.01 minus 12.2 divided by 10.2 into 100. It comes out to be around 17%. This is close to this. Sometimes there are some variations in the options, but you have to choose the close option, that is 16.34 is the voltage regulation. You can see here how easy this question and this type of questions you have done in the class, various questions, numerous questions, also in the assignment. One more question related to ABCD parameters. For the two port symmetric bilateral, if A is equal to 3 ohm, B is equal to 1, find the value of the C. As we know, AD minus BC is equal to 1 and A is equal to D, that means A square minus BC is equal to 1. A square will be equal to 3, that is 3 square minus C is equal to 1. By putting the value, C is equal to 8 Cm, that is this is the correct option. This is how you can use ABCD parameters to calculate all its other values. So this is regarding the sag. A transmission line conductor has been suspended freely from the two towers and has taken the form of catenary, and that the C is equal to 487.68 meter. The span between the two towers is 152 meters, and the weight of the conductor is given. Calculate the length of the conductor. Total length you have to calculate. So as we know, the length of the conductor will always be greater than the span of the conductor, span between the towers on which the conductor is calculated. There is only one option, that is this one. And when you calculate this, you will always find this comes out to be this. As we know that L is equal to capital L, that is the span 1 plus W square L square over 24 into T square. Where W by T is T by W is equal to C. I have replaced T square by W square by C square. So giving the values of known values, you can calculate. It comes out to be 152.615 meter. That is this. So you can also guess its value by having its value, which will be very close to this and greater than this. Another question is regarding the transmission line length. A three-phase 50 Hz 400 kV transmission line is 300 kilometer long. The line inductance is this, capacitance is this. Per phase, assume a lossless line, determine the line wavelength. We need to find out the line wavelength. As I have told you that by looking at the frequency, you can directly get the value of the approximate line length. As we know, for 50 Hz frequency, the line wavelength will be equal to 6,000 kilometers, and for 60 Hz, it is 5,000 kilometers. So you can see beta is equal to omega root of LC. Omega is 100 pi. That is from here. This L is equal to 0.97 milli Henry, and this capacitance is 0.1 millifarad. It is actually microfarad. It's not millifarad over here. It comes out to be 0.0331 radians per kilometer. So lambda is equal to 2 pi by beta. That's 5988. So you can see from here there is no option. You can choose this option for this case. And sometimes these cases arise when the options may not match, and sometimes when the options are given which are wrong. But you have to use your own concept to sometimes correct their options as well. Now, a simple question: what are the type of insulators which are used whenever the conductors are dead-ended and there is a change in direction of transmission line? You know that we have already discussed it is a stream type insulator. One more thing: the sending end and receiving end voltages and the three-phase transmission line at 100 megawatt load are equal at 230 kilovolt. This is the sending end and receiving end voltage which are transmitting a power of 100 megawatt load. The phase impedance is J14 ohm. We have to find out the maximum steady state power that can be transmitted. That's simply Pmax is equal to V square by X. That's 230 square by 14. That comes out to be this. That is the option A. All these questions are asked in the JE 2014 paper. One more question. This is regarding the same transmission line. A 220 volt three-phase transmission line, 60 kilometer long. The resistance is this, and the inductance is this. So using the short model to find out the power at the sending end, the receiving power is given like this. So calculating the sending end power, receiving end current, that is 300 into this. Actually, this is VI is equal to MVA. So that's why I have not used here the power factor. And root 3 because it's again three phase. So 300 into 10 to the power 3 divided by root 3 into 220, it comes out to be 787.3 amperes. So PL, that is the power loss in the resistance, that is equal to 3 into 787.5 square, that's the current, multiplied by 0.15 ohms into 60, that is the 60 kilometer long. It comes out to 16.73 megawatt. So PI will be equal to receiving power, that is this multiplied by this megawatt, that's 300 multiplied by 0.8 plus 16.73. It comes out to be this. But since no option is very close to this, actually when you divide by 3 to this equation, you will get 85.58. Even if it has, sometimes you need to think out of the box and you need to think as per the options what could be the right answer. So actually it has find the power at sending end. It has not mentioned the single phase power. So, but the options are in the single phase power, so you need to divide by 3 to get 85.58 megawatts. One more question, which is very simple question. What's the main drawback of underground transmission system compared to the overhead transmission system? Exposure to the light is not exposed to the light. Heavy initial cost. This is the main drawback of this. Exposure to the atmospheric hazards such as smoke, ice, and wind. This is not the hazard of this, or we can say drawback of underground transmission line. Induction interference between power and communication. This is not this. All these disadvantages are of the overhead transmission line. The main disadvantage of underground transformer is heavy initial cost. So here, what is the power factor of a cable of loss angle E? Usually this figure is not given in the question, but I have given this figure for you to understand. Loss angle E and the power factor angle, they are related like this. That means the summation of these two will be equal to 90. They are complementary angles. So here we are asked to find out the loss angle. We'll find out power factor if loss angle is given as this. This is theta. Loss angle is theta. Loss angle here means delta, which we have discussed in the class. That is delta. You can see we need to find out the power factor in terms of E. Power factor is cos of phi. Cos of phi in this case, but phi is equal to 90 minus delta or 90 minus this theta. When cos of phi is equal to cos of 90 minus delta or 90 minus E, that will be sine of this. Sorry, not E, sine of this theta. This is the correct option. So cos of phi will be equal to sine of this theta. I have also discussed this in the class. So thank you. I think these are enough for this session. These are the different numericals which you may face in the different exams, or similar type of examples you may face in the exam. But I want to discuss these problems before you, so that you will feel comfortable while approaching these problems. You can see almost all these type of problems are discussed in the class, and I hope you will enjoy this class and try to do more types of numericals. Okay, thank you very much. I'll stop.